Hi friends, in this video we are going to discuss about separately excited DC motor. Let's see here. Separately excited DC motor diagram. I am going to draw the diagram. How the diagram? The field winding excited separately. This is the separate voltage source VF. Here the current flowing is IF and this is the field winding resistance RF. And here we have a armature is like this. This is my armature with the voltage, supply voltage V, and here the line current IL, here the armature current IA, but we have a armature parameters, that is back EMF EB and the armature resistance RA. This is the diagram for separately excited motor. That's why it's taking the current. Okay. Next one. What is the current equations from this? Before that, we know torque directly proportional to phi into Ia. But even though the load changes, the flux is constant. So torque directly proportional to Ia is the answer. Very important, this one, for separately excited motor. And next one, speed directly proportional to EB by phi. When the speed is directly proportional to EB by phi, here phi is constant already. When the phi is constant, the speed directly proportional to EB. Yes or no? Yes. So here the speed directly proportional to EB and here the torque directly proportional to Ia. These two are important to draw the graphs. Right. Next one. What is the current equation here? Actually, the current is flows from IL to Ia, right? This is the current flow. So what is here the current equation? IL is equals to Ia. Right? And next one. What is the voltage equation? V is equals to Ia RA plus EB. Yes or no? Ia RA plus EB. From this, EB is equals to V minus Ia RA. From this, Ia is equals to V minus EB by RA. These are the different current and voltage equations. But here some extra drop is there. That is the brush voltage drop. Simply brush drop also is there for V. Right, sir. Next one, what is the power equation? Let's draw the power equation for this. Multiply with current. V into IL is equals to Ia square RA plus EB into Ia plus brush losses. This is simply about the power equation, voltage equations, and the current equations. This is simply the diagram and the mathematics. Okay, from this mathematics we have to go to draw the graphs, which are very important here. So let's go for graphs. So first graph is in between speed and armature current. Let's take it. How it is? For example, take armature current on x-axis and speed on y-axis. See, we know that EB is equals to V minus Ia RA, but we know that EB is equals to K phi N, that is equals to V minus Ia RA. EB is directly proportional to phi into N, right? From that k phi n, I want n. N is equals to V by k phi minus IA RA by k phi. Okay. If IA is equals to 0, if IA is equals to 0, this value 0, then N is equals to V by K phi, which is equals to no load speed. This is my no load speed of separately excited motor. When IA increases, what happened? This drop increases, then the speed decreases. Nothing but from here the speed is reduces. This is the reduced drooping characteristics. This is NIA, the first graph. Next, what is the second graph? The second graph drawn between torque and IA. Are you okay? So let's draw the torque and IA graph. Let's see armature current here and torque here. And we know that torque directly proportional to phi into IA. But here flux is constant. So torque directly proportional to IA. If IA is equals to 0, then torque is equals to 0. If IA increases, then automatically torque also increases like this. This is torque directly proportional to IA. Right. Up to this, everything is clear. But when my IA increases, of course speed reduces, but the armature flux also increases, which leads to increase in armature reaction. If armature reaction increases, the total flux reduces. If the total flux reduces, we know that if the flux reduces, then speed increases. Then speed increases because here flux and speed inversely proportional to each other. That's why this is in generally normal condition when the speed is nothing but this is without armature reaction, this one. But when the armature reaction considered, the speed is like this. This is with armature reaction. This is the no load speed and this is the with armature reaction. This is the without armature reaction. With armature reaction, the speed is greater than without armature reaction. Of course, the no load speed is greater than with armature reaction speed. No load speed, then after with armature reaction the speed, then after without armature reaction the speed. This is simply the speed and armature current with armature reaction. Here also, here the saturation actually we have to consider. But generally in this case up to some extent this increases, but then after goes into saturated level, like this is saturated level is like this. When saturation considered, when armature reaction considered, the speed and torque characteristics are like this. Is it clear? Are you okay? Next one. Next the graph between, next graph in between, third graph is speed and torque. Are you okay? On x-axis torque, on y-axis speed. Of course, I said you the torque directly proportional to IA, so this is also taken as IA, Nothing but speed versus Ia. So how the characteristics? The speed versus Ia and the speed versus torque, the characteristics are similar because torque is directly proportional to Ia. That's why these two are similar. So we have to consider, we are going to draw only two curves. One is for speed, other one is for torque. And the combination, the speed versus torque is similar to speed versus Ia for separately excited DC motor. Right? Is it clear? So this is very important. Separately excited DC motor, they may ask you questions on this. Right? Thank you.